Welcome everyone. In this video we are going to talk about the golden ratio and show how it is related to the Fibonacci sequence. The golden ratio, we denoted with phi, is a number. It is an irrational number. Its value is 1 plus the square root of 5 over 2. And this value is approximately equal to, let me grab my calculator, so I'm typing this value. This is approximately equal to, according to my calculator, 1.618333989. But this goes on forever because it's an irrational number. But this is just an approximation. Okay, so this is the golden ratio. Golden ratio. And what is Fibonacci? What is the Fibonacci sequence? You might be asking. Let's also discuss that, and let's then show how the two are related. Fibonacci sequence. This sequence starts with 0, 1. There is a simple rule to find the remaining numbers. You just add the last two numbers. So you add 0 and 1, that's 1. Then 1 plus 1, that's 2. 1 plus 2, that's 3. 2 plus 3, that's 5. Then you have 3 and 5, so 8. Let me quickly write a few. 13, 21. Let's see, 34. Then 55. Let's write one more. That's going to be 89. This goes on forever. We could express this sequence in a more compact way by using a recursive definition. So a recursive definition is going to have an initial condition, and it's going to have an expression for the next term in terms of the previous terms or a couple of the previous terms, okay? And in our case, it's going to have a definition in terms of the last two terms. So the n plus 1 term is going to be the sum of the last two terms. So Pn plus Pn minus 1. Of course, this definition is not enough. Because what if I don't start with 0 and 1? Maybe I start with, let's say, 3 and 5. Well, let's not start with that. It's like trimming from here. Let's start with, 17 and 5. Then if I use this formula, I would have 22, then 23, then 45. Clearly, this is not the Fibonacci sequence. So I need to specify the initial conditions. And there are two. It is that, it is that P1 is 0 and P2 is 1. So I called this the first term as it is, and this is the second term. And you can see then that the third term is, so to find the third term, you substitute 2 for n here. P3 is going to be P2 plus P1. That is in fact 1. And if we were to find the fourth term, you would add P3 and P2, which is going to give you 1 plus 1, which is 2. Okay, so this is the Fibonacci sequence. The thing is, the claim is, the ratio between successive numbers in this sequence, which we can denote with R, and it is Pn plus 1 over Pn. This ratio, first of all, it is not constant, because we can see that. And also, I want to mention one important thing. We are neglecting P1 in the ratio, okay? So let's say n is not equal to 1 in this ratio. Otherwise, we would be dividing by 0. But for all the other numbers, it's fine. Initially, this ratio is 1 over 1, which is 1. Then later on, it's going to be 2 over 1, which is 2. After that, it is 3 over 2, which is 1.5. Then it is 5 over 3, 8 over 5. So one thing we see is that this ratio is not constant. It is changing. And in fact, it is changing in such a way that it is converging to a value. And I claim that R, so let's say in the limit as n approaches infinity, R converges to phi. Okay, this is the claim. Alright? So this is the claim. And how do we show this? This is the claim. And how do we show this? In showing this, I will be assuming that the ratio is convergent. Okay, if you want to, please write in the comment section if you want to see how this ratio is convergent. I can prove that in a future video, but I need to admit I would need to look it up. I don't know why it is convergent yet. Okay, but with a bit of studying, I think I would be able to manage to show why this ratio would be convergent. So if you're interested in that, please write it in the comment section. But in this video, we are going to simply assume that this ratio is convergent. And we want to show that if it is convergent, it converges to phi. It converges to this number. Okay, this is the aim of this video. And that is the connection between the golden ratio and the Fibonacci sequence. So how do we go about doing this? We have only one equation, right? We only have this. So we should do something with it. And a good way to start is, I think, to divide both sides by Pn. Because if we do that, we are going to have the ratio on the left side. And that's something good, right? We are interested in the ratio. So why not have it in our equation? Hence, I'm going to divide both sides by Pn. When I do that, we're going to have Pn plus 1 divided by Pn equaling 1 plus Pn minus 1 divided by Pn. Cool. Now, the argument here is very nice, I think. The thing is, if we are interested in the limit as n approaches infinity, so let's say the step that we're about to take is valid for the case that limit n is approaching infinity. So what we're about to do is valid for large values of n. For the large values of n, since the ratio is converging to phi, or to any number, right? We assume that it is converging to something, and we will show that that value is phi. So, in the limit, since the ratio is converging to some value, the difference between each ratio gets smaller. So what I'm saying is, like initially we had, as the ratio, we had 1, then it was 2, then it was 1.5, then it was 5 over 3, then it was 8 over 5. These are successive ratios. And as n gets greater and greater, these ratios become closer to each other. And eventually, they will become some value. And that value is going to be the golden ratio. So the thing is, for large values of n, Pn plus 1 over Pn is going to be the same as Pn divided by Pn minus 1. I hope this part is clear. This is maybe one of the most important realizations in the video. And why is this correct? As I was saying, let's do some other example to maybe make this more intuitive. If we have a sequence like 1.9, then 1.99, then 1.999, then 1.9999, you get the idea. It is 1.9 repeating basically, you get the idea. This is converging to 2. And as you can realize, initially there is a finite amount of difference between the two numbers. The difference is in fact 0.09. Then it is 0.009. Then it is 0.0009. So the difference is becoming smaller and smaller. And eventually, since the sequence is converging to 2, the difference will become 0. So the two consecutive terms to the two consecutive numbers will essentially be the same. And this is the argument that we're making for our case. We have a sequence for the ratios, right? And let's even write the sequence of the ratios. So ratios, let's say. We start with 1, then 2 over 1, that is 2, then 3 over 2, 1.5. I'm going to write them quickly. So 5 over 3, that is 1.6 repeating. I'm using a calculator, by the way. I don't do this in my head. 1.6. Then what else? This is going to be 1.625. Then 21 over 13, that is 1.75. I hope I don't miss a step. If I do, excuse me for that, but the general idea still holds. Okay, so 1.619. Let's continue on the new line. I'm going to do a couple more, okay? Don't worry. I'm not going to do this forever. Because I could go on forever. But why would I? 7, and then the last one is 89 over 55. Last one that we're going to do, but that's what I mean. And that is, well, that is this actually. Interesting. Okay. So already, I mean, the observation is already we see that the ratios are getting closer to phi. That's an observation and it's valid. I mean, that might satisfy you, but in a couple of minutes, we're going to have a much more satisfying evidence that the ratios, in fact, converge to the golden ratio. So, yeah, what was I? Yeah, why did I write these ratios? Well, because I want you to see that the ratios are getting closer and closer to each other because they are getting closer and closer to some value. They are converging to some value, so they must get closer to each other as well. And there is a, jumping off up and down, like it increases to 2, decreases, increases, decreases, increases, decreases, increases, then decreases, maybe increases again. So there is jumping off initially, but after a while, the value stabilizes, the value converges. Cool. So I hope this claim makes sense to you. And realize this. I emphasize we are assuming convergence because if we are not assuming convergence, we can't really say this. And if we can't say this, we can't do the derivation. So convergence is assumed. We are not showing that the ratios are converging to something. It definitely looks like they are converging to some value. So this statement is not very outrageous. It makes sense, but still mathematically, it is not that sound. It isn't proved in our video. Okay? It is assumed in our video. So convergence lets us say this very powerful statement. So let's move on then. What can we say? Well, this is going to be R. I'm quoting here. This is R equaling 1 plus. And notice we have Pn minus 1 over Pn. This is the reciprocal of our ratio, so it is 1 over R. If I multiply both sides by R, it is going to be R squared equaling R plus 1. So it is R squared minus R minus 1 equaling 0. If we solve for R using the quadratic formula, it is going to be 1 plus or minus 1 minus 4 times 1. This became a plus because of this minus. We divide by 2. It is going to be 1 plus or minus the square root of 5 over 2. And we are going to neglect the negative root because 1 minus the square root of 5 would give a negative number. And that doesn't make sense for our case. All of the numbers are positive. The ratio must be positive. So R is 1 plus the square root of 5 divided by 2. Right? And this is, in fact, as you can see here, the golden ratio. So we showed that if the ratios in the Fibonacci sequence, and by the ratios, you know what I mean this ratio, that ratio converges to the golden ratio. But please understand, I emphasize it one more time, we assumed convergence, and based on that assumption, we were able to show that that value of convergence is the golden ratio. Anyways, I hope this video was helpful. If you have any questions, please add them in the comment section. I hope to see you in another video. So for that, please make sure to subscribe. So see you in another video. Until then, take care.